OPRA, which stands for Online Preference Reporting and Aggregation, is an online open source system for group decision making. We will illustrate OPRA's distinctive features, including the voting interfaces, preference analytics, and group decision making in combinatorial domains. We will also discuss our recent work in an automatic student mentor application system. OPRA includes 5 different interfaces for users to report weak orders over alternatives: 1-column, 2-column, slider, star rating, and yes/no. The 1-column interface allows users to perform drag and drop operations to submit their rankings over the alternatives. This optionally supports ties, allowing either weak or strong orderings to be submitted. The 2-column interface is similar to 1-column, but allows some alternatives to be unranked. All the alternatives start in the right column as unranked, and the user chooses which ones they would like to give a ranking to by moving them to the left column. The left column behaves identically to the 1-column interface, allowing users to give their ranking. Alternatives that remain in the right column are submitted as unranked. The slider interface allows the users to rank each alternative from 0 to 100 using a slider. The star rating interface allows a ranking of 0 to 10 using a number of stars. Finally, the yes/no interface lets alternatives be ranked in a binary manner. Each alternative is ranked as checked or unchecked. The results of polls are shown in a table of different voting rules. This gives insight into the poll data. OPRA includes many voting rules, including plurality, BORDA, K-approval, single transferable vote, and other rules seen here. For each voting rule, a score associated with each alternative is calculated and organized in the table so that users can check the winner of the poll under different voting rules. The square color indicates the score for that alternative. The greener it is, the higher it is ranked. The specific voting rule chosen by the poll creator is highlighted, indicating the actual poll result. OPRA also computes the margin of victory for some voting rules. Margin of victory measures the robustness of the voting outcome, and also plays an important role in post-election audits. The higher the margin of victory is, the more robust the outcome is. Underneath the table, OPRA shows mixtures, implementing the Enhanced Gaussian Mixture Model, or EGMM method, of learning mixtures from the Plackett-Luce model. The mixtures offer a high-level overview of groups and the strength of their preferences based on users' ordinal preferences. They can be used to make useful decisions such as group activity selection. To aid in complex sequential polling over many alternatives, OPRA provides a system to allow users to set up multi-polls. These multi-polls allow users to submit their preferences either traditionally by waiting for the result of a previous poll, or by using a conditional preference network, or CPNet. This graph expresses a user's conditional preferences over alternatives based on the possible winners of previous polls. The interface allows the user to rank alternatives and then indicate whether their ranking is dependent on previous polls. If so, they can then specify their preference in each possible winner case of the parent poll. A dependency graph is also generated and shown in the interface. The 2-column voting interface is used in the preference entry, allowing for ties and unranked alternatives. OPRA offers an online mentor application tool to automatically assign student mentors to courses looking for mentors. The matching is based on the kinds of mentors a course is looking for and how much a student wants to mentor that course. On the student side, students who desire to be mentors can submit their application. They fill out their information, including their name, GPA, and the courses they are qualified to mentor. Then, on the next page, the student uses the 2-column interface to rank the courses they selected in their order of preference. The higher ranked a course is, the more the student wants to mentor that course. If a student does not want to mentor a course, they leave it as unranked. From their page, instructors are able to modify the feature weights of their course. These weights affect how important things such as GPA or mentor experience are when looking for mentors. These weights are used within the matching algorithm. The instructor can also recommend or unrecommend students. The matching algorithm works as follows. For a given course, we calculate a student's score for that course as the dot product between the course's weight vector and the student's feature vector. This is done for each student, the resulting score is giving a preference ranking over all the students for this course. We then use these course rankings over students and student rankings over courses to run the Gale-Shapley stable matching algorithm, with the courses proposing and also having a max capacity. The Gale-Shapley algorithm ensures the result is stable. From the administrator page, the matching can be run. The results are shown, and then they can also modify weights, add, remove, or fix students through the ranking interface, and perform real-time rematching. The system also supports some explainable AI functionality. From their page, administrators can view reasons why a given student was or was not assigned to a given course. For example, a student wasn't assigned to the given course because they were instead assigned to another course that was ranked higher by that student. We have just shown the current functionality of the OPRA system. It is open source, which makes it easy to make changes. As always, there are areas for future work. With OPRA, we would like to expand into these three key areas. Usability. We would like to improve OPRA's human-computer interaction. This includes work such as offering probable initial rankings to users without introducing bias in poll results. Explainability. We would like to add more comprehensive analytics and statistic tracking to OPRA in order to improve the explainable AI functionality. Algorithms. We would like to improve the algorithms OPRA uses, both for polls as well as mentor matching. Better poll mechanisms could aid in group activity selection and group decision-making, while a better matching algorithm would be able to handle min-max bounds to course capacity.